increased cyclic AMP was also shown to prevent PSD95 deficits after an excitotoxic injury. So these observations propelled us into our final study, where we will characterize the therapeutic efficacy of PDE4 inhibitors against heretofore discussed alterations induced by primary blast exposure. We observed that PDE4 inhibition prevents blast-induced LTP deficits. We exposed cultures to level 4 blast and then immediately treated cultures with either a DMSO vehicle, PDE4 inhibitors, which include roflumilast, piclamilast, or ibutilast, or a PDE10 inhibitor known as papaverine. We report percent potentiation on the y-axis and the respective drugs and their concentrations on the x-axis. And we found here that therapeutically relevant concentrations of roflumilast at 1 nanomolar or higher were able to prevent losses in LTP after blast injury, as compared to a blast plus vehicle or a blast plus a low concentration of roflumilast at 100 picomolar. The other PDE4 inhibitors exhibited a similar effect, shown by here and here. However, the PDE10 inhibitor, papaverine, was no different than the blast plus vehicle group, which you see on the far right. This demonstrated that the observed preventative effect is specific to certain phosphodiesterase inhibitors, which includes PDE4 inhibitors. Next, we investigated the therapeutic window provided by one of the PDE4 inhibitors, roflumilast. We chose to specifically move forward with roflumilast as it is already FDA approved for the treatment of chronic obstructive pulmonary disorder, or COPD. Following level 4 blast, we delivered either vehicle or 1 nanomolar roflumilast, which was the minimum therapeutic concentration we identified previously, to cultures at increasing time points after injury, 1, 6, and 23 hours, which you see on the x-axis here. Again, we're reporting percent potentiation on the y-axis. And if we compare blast plus vehicle to blast plus roflumilast, we see that delivering the drug up to 6 hours post-injury was effective at preventing LTP deficits. However, delivering this drug at 23 hours following injury showed no significant effect. This indicated that the therapeutic window of phosphodiesterase 4 inhibition is between 6 and 23 hours, beyond which PDE4 inhibition cannot rescue primary blast-induced LTP deficits. So finally, we found that roflumilast treatment prevented changes to expression and phosphorylation of the key proteins that were influenced by blast in AIM-3. So again, here we're looking at total PSD95, phosphostargazin, phosphogluor1 at the serine A31 site, and total GLUR1 expression. We exposed the cultures to level 4 blast and then treated them with either vehicle, which we show in black, or roflumilast at 1 nanomolar in white, delivered at 6 hours, so we're using the minimum therapeutic concentration at the maximum therapeutic time of delivery. And we observed that roflumilast treatment significantly elevated total PSD95 expression regardless of LTP induction as compared to blast plus vehicle. Drug treatment also elevated stargazin phosphorylation when LTP was induced as compared to blast plus vehicle. It's important to note that blast exposure prevented an increase in stargazin phosphorylation when LTP was induced for the blast plus vehicle group, which matches our findings that we reported in AIM-3. Next, we observed that blast plus roflumilast exhibited elevated GLUR1 SER831 phosphorylation when LTP was induced as compared to blast plus vehicle. Again, as with stargazin, this prevented an increase in phosphorylation of this site when LTP was induced for the blast plus vehicle group, again matching our results from AIM-3. Finally, roflumilast significantly elevated total GLUR1 expression with LTP induction as compared to blast plus vehicle, shown here. So to summarize, phosphodiesterase 4 inhibition after blast exposure exhibited multiple therapeutic effects on both electrophysiological function and protein expression and phosphorylation. We found that blast-induced deficits in LTP were prevented by roflumilast when delivered within 6 hours following injury. The threshold for therapeutic benefits from roflumilast exposure existed between 6 and 24 hours following injury. Military missions can often occur over the span of several hours, so an extended treatment window would be ideal from a therapeutic. We found that delayed roflumilast delivery also reversed deficits for the key LTP proteins, including PSD95, stargazin, and GLUR1. Our hypothesis here is that roflumilast treatment prevents PSD95 degradation This allows for proper immobilization of AMPA receptors at the synapse, subsequent phosphorylation of GLUR1 at the serine A31 subunit, serine A31 site, and thus LTP induction can occur. As I previously mentioned, roflumilast is already clinically approved for COPD treatment. Coupling that with the positive results that we observed in this study, and roflumilast is a therapeutic candidate that warrants additional animal studies following in vivo blast injury. So to conclude the presentation, I wanted to refer back to the slide where we laid out our strategies to reduce BTBI. We can now see how these findings that we reported fit into these strategies. In aim 1, we observed that primary blast deforms brain tissue in a low strain, high strain rate manner, which validated previous computational modeling of our injury device. In aim 2, we identified both strain-based and impulse-based thresholds for neurological dysfunction following primary blast, which specifically identified LTP as a highly sensitive measure for primary blast-induced neurological dysfunction. These findings will improve computational models of BTBI and provide helmet researchers with design criteria for improving military helmets. In aims 2 through 4, we reported blast-induced LTP deficits developed between 1 and 24 hours following injury, with the potential to recover within 6 to 10 days after blast. We also reported a therapeutic window for intervention existed between 6 and 24 hours following injury, and these findings can advance critical care practices for military medical professionals in theater, providing information on symptom onsets, therapeutic intervention, and therapeutic intervention timelines, and proper rest periods. We also explored the cellular mechanisms for dysfunction driven by disruption to synaptic proteins, specifically PSE95 degradation. We also presented an exciting therapeutic FDA-approved roflumilast to remedy the negative effects observed by primary blast, both functionally and at the protein level. These findings provide researchers with a potential pathway for preventing memory loss following blast exposure. There are several limitations to address when considering our conclusions, however. Excuse me. Our conclusions are limited to only the hippocampus and may not reflect how other brain regions respond to injury. Given the age of our tissue samples, they have been equated to studying the human juvenile's brain response to injury, so it will be important to keep in mind that developmental changes in the brain can influence injury response. We used an in vitro preparation of rat brain samples, so we cannot make direct comparisons of our data to behavioral changes in vivo or to overall experiences of the soldier. Our studies are limited to investigating the effects of a single isolated primary blast with discrete blast exposure levels. In reality, soldiers are facing blast exposures in tight and urban environments or in vehicles where waveforms can be distorted by reflections. They can often face multiple exposures in succession or end up varying intensity. So these are things to consider when analyzing the data. Finally, roflumilast at 400 Daltons is too large to readily pass the blood-brain barrier, which typically limits molecules above 376 Daltons. This could be an issue for oral delivery of the drug. However, this may now actually be a limitation in this specific situation, as research from our own lab has found that blast-induced DBB opening occurs in the order of 70 kilodaltons at 4 hours, up to 4 hours post-injury, which would allow for roflumilast to pass in that situation. So findings from our studies suggest other future studies that could be pursued. As I just mentioned, we only investigated single Friedlander-like blast overpressures, and it will be important to know the effects of more complex waveforms. Additionally, future studies will be needed to determine the effect of combined primary, tertiary blast in vitro. While we only investigated hippocampus, future studies are necessary to determine the effect of blast on alternate regions like the cortex, cerebellum, amygdala, and the brainstem. While we demonstrated changes in electrophysiology and protein expression following injury, future studies are necessary to determine the corresponding histological or structural changes that are associated with blast. In aims 3 and 4, we propose that PSE95 degradation drives downstream protein deficits and LTP dysfunction. Future studies will be needed to determine the cell process that degrades PSE95 following injury and the cell process that prevents blast-induced PSE95 loss following PDE4 inhibition. Lastly, greater translational studies are necessary to examine the effect of primary blast in vivo, specifically in examining other phases of blast along with primary, induced behavioral changes, therapeutic rest periods, and possible possible pharmacological interventions, including roflumilast, that can better relate the blast injury sequela to the human level. So to wrap up, during my time at Columbia, I've contributed to 9 peer-reviewed publications, including 4 first-authored papers, 2 of which have already been accepted. 1 is currently in revisions, and 1 is being prepared right now. I've also written a review chapter. Additionally, I've contributed to a total of 13 conference abstracts and proceedings over the years. And the last part, I just wanted to take a moment to acknowledge the people who have helped make this work possible. I'll start out with Barclay, my advisor. Over the past 5 years and change, I've definitely learned a lot from you. You really guided me and provided a lot of mentorship. You've really shown you've held a high standard of work, and I think your students will all agree that it really helps them rise to the occasion and produce better work. I also really want to thank you for making yourself very available, which sometimes professors don't do that. You're always willing to look through data. You're the first one that's willing to roll your sleeves up and go into lab when something's not working and needs to be fixed, which is somehow frequent for us. I mean, we're blowing things up, so I guess that makes sense. And I think all of our students can agree that we really appreciate everything you do for us, and you've really provided a good influence, so thank you for that. I want to thank everyone in lab, both past and present. You guys, through discussions, random discussions, whether it's lab related or not, we really depend on each other to get through the time here. And I think our lab is unique. One of the things I really enjoyed about it when I was interviewing here was that it felt like a real support system for each other. Everyone got along really well. We are a bunch of big personalities, and I think that reflects our advisor as well. I want to thank our collaborators at Duke and Penn, who are part of the Muri grant, which funded the majority of this research. Dr. Meany was at the University of Pennsylvania. It was great to be able to go through our data every other week at our teleconferences to really understand and parse through and understand what we're doing. I want to thank the thesis committee for taking time out of your day to come sit here and listen to me ramble on for what I've done over 5 years. I want to thank my friends and family, those that are here, both from Columbia, from home, from undergraduate, and those who also couldn't make it. I especially want to acknowledge a few people. First, my fiance Liz for being here. I also first want to apologize because I don't know how many times I've texted you to say I'm leaving lab in 10 minutes, and sure enough, 90 minutes later, I send you the same text message because I get caught going down some rabbit hole. I just want you to know that it wasn't for nothing. It went to this presentation that you have to enjoy right now. So
you did warn me on the first date, so.
Can't say you didn't get fair warning. So. Also, just all the support and love that you give me over the time we've been together has really helped me get through this work and produce this. So thank you, and I love you. And I also want to thank my parents, Ed and Melanie Vogel, who are here. I want to do that through just a quick story. I don't know if they remember this. They're eye-rolling because they think I can tell quick stories.
Okay.
I don't know if they remember this, but in first grade, I had to
go back.
In first grade, we had an arts and crafts homework assignment where we had to make this little person that was representative of what we wanted to be when we grew up. And when I say I designed this, it was most likely my mom because this was 80% her, but I'm sure I consulted on the direction. It's arts and crafts. I'm not doing arts and crafts. So my guy had a lab coat on, a test tube in one hand with like cotton balls, smoke coming out of some random yellow liquid, which I don't know what that would be, and an Erlenmeyer flask in the other hand. So I wanted to be a scientist. And I know without the lessons that you guys have taught me over the years, the hard work and perseverance that you've instilled in me, this work wouldn't have been possible, all the love and support that you guys have given me over the years. So I just want to say thank you for that. Thank you from me and from first grade Eddie for allowing this to come true. And I just want to say that I love you guys. And with that, quick story's over, thesis is over. I want to thank you guys for your attention and open the floor to any additional questions you might have.
Okay, so have some time for some questions from the audience.